So I just wanted to say what the Riemann curvature. So we had this curvature tensor, right? And so I guess what we have to do is we have to actually specify two derivations. And what we said was this was the commutator of these guys minus the one associated to the commutator. Okay, so this is the Riemann curvature tensor. So let's take x I. So this will be local. So this is a local set of parameters. System of parameters for S. So our base space S. And so these aren't raised to a power. So these are, again, I'm just going to write them like this. And then what we'll do is we'll take omega, and we'll be able to write omega as a summation of AI dxi's. So these guys are scalar, and then this summation is going to be implied. Okay, so again, I runs from 1 to n, and n is the dimension of S. And I'm going to, and then, so I want to compute this, what this looks like in coordinates. So in coordinates, so let's say that these are, so let me say that, let's take a basis theta 1 through theta, let's say up to n, and it's going to be the dimension of our space. Let's say these are d dx1 to d dxn. Okay, and E will use the notation that these guys will be denoted like so. And these derivations in this case, these are what are so-called homothetic. And this is just a complicated way of saying that partial derivatives commute. Di dj is equal to dj di. So that they do like this. So this is one. So like you can. There's a certain nice choice of derivatives. There's other nice choices you can make. This is a particular nice one, and this does this. Okay, so in general, these ones will be homothetic if theta I and theta j commute, and they don't necessarily have to look like this. Okay, so let's look at the curvature tensor in coordinates. So since they're homothetic, so this is the same thing as saying that di and dj are 0. So okay, and then we'll take this guy to be defined to be equal to the covariant derivative with respect to the ith parameter, and then we're going to take this. We're going to look at what this commutation looks like. Okay, so this is here. J like so, and recall that this guy here is really just this. So this is the formula for the covariant derivative, and so now we're just going to apply this everywhere. J here minus Ji. Okay, J plus J. Okay. Now what we need to do is so let's write this with compositions so this becomes more clear what's going on. We need to use some kind of the product rule. So again, these are all operators. So so notice that so if we have a partial derivative and we have a matrix, and then we apply it to some function or some vector, what we're really going to be doing is we're really going to be taking, so we take dB, and then we apply v, plus b, and then we do times dB, dV. Okay, so what this is really doing is this tells us that D composed with B. So this is like in the kind of like endomorphism algebra. So this guy here looks like D applied to B plus B before D. Okay, or after applying D. And so this is just comes from the product rule. And this partial here just denotes a derivative. Okay, so this is kind of like a little side work here. And now I'm going to use this to compute what things are. First, let's kind of expand what things are. And so here we're going to have D composed with so this one, dj, plus di composed with aj, plus so plus this guy and this guy, plus this guy and this guy. Okay, and this is just going to be matrix multiplication plus the antisymmetric of the same thing. Okay, so we flip I and j and we take a minus sign. Okay? Or we can say minus flipped. Okay. So then what do we get? So this thing becomes, so this is just di dj. Here, plus, now we have this guy. Now here we have to use the product rule. So we do this. Okay, so what do we have? We have di aj plus aj di plus, and now this one's just ai dj, and then we have plus ai aj. Okay, and so the antisymmetric part is we have the exact same thing but with flipped indices, dj di minus dj ai minus ai dj minus aj di minus aj ai. So these go away. These go away. These guys go away because equality of mixed partials. And then we're left with this guy here. And this gentleman here. And this is the commutator of ai and aj. Like so. This part here becomes easy, so let's make some notation again. Let's make some notation. Theta I is going to be, or sorry, nabla I is going to be this. Okay, and so now what we can do is we can start to compute what this thing looks like. Di and for di and dj, this guy will be these, and then this will be minus this guy. Okay, and this thing goes away because of this relation here. And that allows us to just plug in our formula that we derived earlier. So as operators, this guy just looks like di aj minus dj ai plus ai aj. Okay, that's all I wanted to say about that. I'm going to pause the video and be back.